All right, so we're going to talk about maximization and minimization. So, when do you want to maximize something versus when do you want to minimize something? Um, this can occur with any type of function, right? So, you think about how the y values work. You can have big y values, little y values. Do we want small ones or do we want big ones? It depends on what kind of problem we're trying to figure out. So, we'll go through a couple examples, but just think of a graph. A normal graph, like a large cubic graph, could look something like this, where it extends off. If we only look in a certain area, like if we look within this area, which oftentimes in the real world our domain is kind of restricted. We can't use too many things, or we're limited to a certain little area that we're looking at. We can see that, there's certain features of our graph that create either maximums or minimums. And so the variable that we're changing changes what happens with our function. So what we're going to try and figure out is how do we use functions to figure out real-world problems and how to solve things to maximize or minimize something for ourselves. So let's take a look at a very typical problem at first, so you can kind of get an idea of what I'm talking about. So the first problem that I'm going to look at is, so we have this big square or big cardboard piece, okay? And we're going to try and turn it into a box lid. So we're going to cut out corners. So if you can see the corners here, we're going to cut out a corner. And what we're going to do with that is that we are going to fold it, and after we cut it, and then we are going to create our box. So we have at first the dimensions of our big square or a big cardboard piece. It's 24 by 24. Now you'll notice this happens a lot with these types of problems, that they have 20, this whole thing is 24 long. Now we want to figure out how much do we cut off each side in order to create this maximum volume. Okay, so one of these squares, if we cut it off, fold in the sides around it, it's going to create a open box, an open topped box. So if that's 24 to start, and we want to know how much we want to cut, they use x as the unknown of how much we're going to cut into each side. So when we cut in that much to each side, instead of it being 24, we take x away from one side, we take x away from the other side, and we create, now the box will have a width of 24 minus 2x. So it's going to be a little smaller than the original, which makes sense. When we fold it up, that'll happen. Okay, so when we do the same thing to the other side, again, we end up with 24 minus 2x. So we know that if that side was 24, we take away 2x, we end up with the same thing. Now, a box is going to have a height as well, or this volume. And so the volume of that, when we take away x, obviously, each of these lips is going to be x. And so the height of this is going to be x. So we have a volume now, right? So we know that volume equals length times width times height. So we're going to build this function, and I'm going to show you how we can figure out what value of x is going to give us the most volume that we can hold within this box. Okay, so the first thing we're going to do is write our volume equation. So our volume equation, which was length times width times height, is going to be our length, which is 24, minus 2x, our width, which is 24, minus 2x as well. So that's just a coincidence for this particular problem. And then our height is just going to be regular x. So what we're interested in is, this is a function. So we want to figure out what is the maximum value of this function. So when we think about maximums in terms of calculus, what we have to do is we have to find our critical numbers and then figure out whether those are maximums or minimums so that we can know where those things occur. So in order to find a critical number, we first have to find the derivative. So this function here is it's factored right now, which isn't really great to find the derivative. So what we're going to have to do is we're going to have to go ahead and simplify this down to kind of a general polynomial form. So I'm going to multiply these two things together, and then I'll multiply by x afterwards. So I'm going to get my volume to be 24 times 24 makes 576. My outside term is going to be negative 48x. The inside is negative 48x, so I should get negative 96x from those two. And then lastly, the plus 4x squared, which is negative 2x times negative 2x. So I get that times x. So that's going to lead me, after I multiply my x back through, that I'm going to have 576x minus 96x squared plus 4x cubed. So at this point, I've got my derivative. Now I want to find my critical numbers. Okay, so I'm going to go ahead and try and solve this for when it equals 0. Okay, so what I'm going to do is say that, this should be, I apologize, this should be v prime, because I actually, oh no, it's not. I'm crazy. Now I need to find my derivative. I'm skipping ahead. So my derivative of this function is going to be v prime equals, so 576x just becomes 576. Negative 96x squared, I multiply my negative 96 by 2, and I get negative 192x. My 4x cubed becomes 12x squared. So I want to now figure out, when does that equal 0? Well, one thing I do notice is that all of these terms, and you may not see it initially, all these terms have 12 inside of them. So this is the same thing as 12 times 48 minus, let's see, that is 16 times 12. And of course, 12 times 1 is x squared. So what I'm going to be led to figure out here is that this is going to be the equation I'm going to try to use. The number 12 can never make 0, so I don't even have to worry about that. But now I can say that, well, x squared minus 16x plus 48 equals 0. So what values of x make that happen? Let's figure this out. So if I factor two numbers that multiply to make 48, that add to make negative 16, are negative 4 and negative 12. This leads me to say that my x values, these are my critical numbers, by the way, are either going to be 4 or 12. Now let's think about what that means for the original problem. Now this is really important when we talk about real-world problems. Let's look back up at the top. So my volume says that my width, or my length and my width, are both 24 minus 2x. Well, if I use 12, there will be no width at all, or length, right? Because those will both be 0. 24 minus 24 makes 0. This is not going to be a critical number for me. That's not going to give me any volume at all. It'll just be flat, right? And actually, it'll just be really weird looking. So I can use 4. Now, what I'm going to do at this point is I'm going to move to another slide. And so I know that my volume equation was 24 minus 2x times 24 minus 2x times x. And I know that my critical number that I found is 4. So what I want to do is that's the only critical number. So now I have to check the endpoints. What values of x am I actually allowed to use, right? What are the earliest numbers and what are the last numbers? Well, if I don't, I can use x equals 0. Because if x equals 0, that means I don't cut out of it at all. Well, that's pretty easy to tell that my volume is going to make 0. Because my volume would be 24 times 24 times 0, and that equals 0. So this is where I'm checking those endpoints to make sure that there's no other place where this can happen. Now my other endpoint, the biggest number that I can use, is 12, because if I use a number bigger than 12, I don't have the ability, I can't have a negative length, right? I can't have a negative length. So that's the only one I can use. Now this would end up making a volume of 0 times 0 times 12, which is also 0. So I know that this x equals 4 is going to either give me a maximum or a minimum volume. It's pretty easy to see that it's going to actually be a maximum volume. So if I were to say when x equals 4, then my volume is going to equal 24 minus 8, which is 16. Then I have 24 minus 8, which makes 16, and then that's 4. Well, 16 times 16 is 256. If I multiply that by 4, I should get 1,024 cubic units of whatever I'm using. So that's the biggest volume that is possible using these restraints, right? So I can't move before or after. So that's kind of the crux of how the maximization or minimization problems work. So here's a list of a way to make more sense. So you can pause this if you want in just a second to write these down. It would be a good idea. So what you want to do when you think about these is you want to try and figure out everything that you are given and everything that you need to figure out. All right? A sketch will really help with that. So if you make a sketch, that will kind of lead you in the right direction. So that's what I had. You need to write the primary equation for what you're trying to maximize or minimize. So if it wants the maximum volume, or if it wants the minimum area, or if it wants the minimum distance or something like that, then you need to know that that's your primary equation. I need to use the distance equation. I need to use a volume equation, so on. So what you want to try and do after that is get that one particular formula that you're using down to one independent variable. So sometimes you're actually going to end up with multiple variables that you're going to be using. You have to get everything in terms of one. So that is different depending on the problem, but once you have your primary equation, then you'll know which one you need to remove. After that, once you go through and actually figure out, steps 4 and 5 are kind of, you can kind of mix them up. You can go ahead and find your critical value, but then always go back and think about what the domain is. Otherwise, you can start with what's the domain, then you can go and know which critical values to ignore. So once you do that, then you can always plug it back in depending on what kind of problem it's asking, and you can get your answer. So here's a list. If you need to look back at it, please just pause and write it down. Otherwise, I'm going to move on. So another problem that you might run into is something like this. So there's a farmer that is trying to fence in an area along a river. So what he wants to do is he wants to cover a particular distance. He wants to have a certain area, but he wants to use as little fencing as possible. So there's lots of options for that, right? You can think of a skinny rectangle, where it has a lot of the river, or a thin rectangle that has a little of the river but a lot of the land, or something in the middle. So he doesn't know how far from the river he calls y. He doesn't know how far from the river he's going to run his fence, and he doesn't know how long along the river he's going to run, which is x. So these are two different variables that we do not know what they are. But if we have some information, then we can go forward and figure out exactly what we need. So the problem is a farmer wants to make this rectangular pasture. He wants it to contain 245,000 square meters in order to provide enough grass. So we don't need any fencing along the river. So what it's saying is that what dimension can he use that will require the least amount of fencing? Okay, so what's the least amount of fence that he would need to use to cover this? So let's see what we have at first. So it says that it must contain 245,000 square meters of space. So we know that the area involved has to equal 245,000 square meters. Okay? Now, what we need to know is the perimeter, right? The perimeter of the fence. We do not know that. We want to know the minimum perimeter, okay? So what we need to figure out is how do we set up a perimeter equation, okay? So the perimeter here, based on my drawing, we can see the perimeter of my fence. I'm going to write this under the fence. Very simply is x plus 2y's. That's it. So we're going to try and minimize that function. Now, if you remember from earlier, this is our primary function, p, perimeter. We want to minimize that. Now, we have two variables, right? We need one. So we need a way in order to write one variable in terms of the other. So the way we use that is with this 245,000. Now, we know that the area of this is the same as x times y. Because if we do x times y, it'll give us the area of this rectangle, right? If that makes sense? So now what we need to do is use this number, and we're going to replace one or the other. Now, I'm going to replace y in terms of x. So it's pretty simple, right? So if I divide both sides by x, I'm going to get y equals 245,000 divided by x. Okay? That's it. So now I can kind of put these two things together and create a new formula that says that my perimeter is the same thing as x plus 2 times 245,000 over x. Because I know that the area has to be a certain thing, there's a relationship between how the lengths and the widths have to work, right? They have to multiply together to make that 245,000. So there is a relationship they have to each other. So that allows me to replace y with something in terms of x. So what I am going to do is move along real quickly and write this slightly differently. So my perimeter equation was the same thing as x plus 2y's, which I'm going to simplify that as now it should be 490,000 over x. So that's 2 times the 245,000. And I'm going to write this just a little bit differently as well, just to make it easier to do the derivative. I'm going to write this as 490,000 x to the negative first. It'll help make things make more sense in a second. So as I go from here, I'm going to find my derivative. I want to try and find what value, my critical values. So my derivative is going to be p prime equals 1, the derivative of x. Now this is going to be plus negative 1 times 490,000 times x to the negative 2, which is the same thing as 1 minus 490,000 over x squared, just to make it a little simpler, right? So that's what this looks like overall. Now what I'm trying to figure out is when does this guy equal 0? So I'm going to say 1 minus 490,000 divided by x squared. That is going to equal 0. Now if I know that that equals 0, then if I use this equation, I'm going to move one part over. So I'm going to get 1 equals 490,000 over x squared. Now this would be pretty easy to see that x squared would have to be the same as 490,000. Okay? Now the square root of 490,000 should be, so we should get either positive or negative 700, technically meters. Remember, that's an option in some problems. Now, in this problem, it doesn't make sense for our x to be negative 700 meters. So we're pretty much going to go ahead and say, this doesn't make sense. X equals 700 meters. So that gives me one part of what I need, right? Not everything. So I know that my x is going to be 700 meters. Now I need to figure out what y is going to have to be. So if you remember from earlier, we knew that my area had to be 245,000. And that was the same thing as x plus 2y. Or excuse me, incorrect, x times y. And we said that, well, y would therefore be 245,000 divided by x. So if x happens to be 700, then that would mean that y is going to equal 245,000 divided by 700. So 245,000 divided by 700 gives me that y would equal 350 meters. So the dimensions that what I'm trying to do is that my x value is going to be 700 meters. My y value is 350 meters. And so when we look up here, we see that this is 350, right? We see that y is 700, right? And we see that, or x is 700, and we see that the other, again, y is 350 meters. Now, this is an odd rectangle. You're like, wow, why did it work this way? Well, in reality, and you'll notice this through some of the problems, the most efficient shape for perimeter, if we're using a square, the most efficient way to make like a rectangle with the least amount of perimeter is going to be a square. Now you may say, well, this isn't a square, right? But we're missing a side. We're missing this side altogether. So imagine for a second that we had another one of these. Well, if this was 350 and this was 700 and this was 350, we would have a square of 700 by 700. But because we're missing that other side, it kind of breaks that slightly. But the big goal, again, going back to the beginning of the problem, is we want to figure out what is it we're trying to minimize. We wanted to minimize the amount of fence or the perimeter. So everything goes from there. Now, the extra info that they give us allows us to write y in terms of x to allow us to happen. So when we go over these in class, try and keep in mind what is the thing we're trying to minimize, and sometimes we do have to do a little work to make that happen for us.